So in the future, when you're trying to read the colour codes off these resistors, you only have to remember BED, bed. So I'm just going to go through all these resistors now. I'm going to find out how good or how bad they are, and then we'll decide what we're going to change out. So I'll bring you back when I've gone through all that. Well, I've actually only got to resistor 2, which is actually a variable resistor. It's our volume control here, and hopefully you can see on the digital meter that it's actually it's jumping around everywhere. This potentiometer should be about 50k, and well, let's go end to end. So that's 58, so it's a little bit above what it should be, but again, we're not worried. But let's just go back to that wiper connection. And I think you can probably see that's just jumping around all over the place. But you can see that that's going to cause us no end of problems. So it's going open circuit. The wiper obviously isn't making contact. I've already tried spraying some of this deoxit into it, and the control hasn't responded at all. It didn't help. So I think all we can actually do at this stage is we're going to have to take this out and undo it and see if it responds to being being cleaned out properly, and maybe we can actually bend the wiper and make a better contact with the carbon track inside here. These sort of pots in valve radios, they're usually damaged because a capacitor has failed and they've managed to get some AC onto them, which kind of burns away the track, it eats away at it. Now when you're working on old valve radios like this, a really high power soldering iron is a godsend. It's pretty much essential because the wiring and everything, all the components, are physically very big and they just draw a lot of heat away. So luckily this paste soldering iron is it's quite a powerful old girl, so shouldn't have any problem undoing any of these joints. Now when I was trying to unsolder this, I was actually kind of using the end of the soldering iron like a bit of a crowbar, because you'll find that these wires, these single core wires, they're fairly heavy cage and they take a lot of bending, and they're actually wrapped around the terminals. They go through the hole and wrap around, and they can be quite difficult to undo. What I would say is if you're really struggling to undo them, the best thing you can do is just cut them off, because what you don't want to do is spend a lot of time putting more and more heat into something and maybe break a terminal off or actually damage the component. So if you're really struggling to get these things off, just cut them off and put a new connection in afterwards. It's the easy way to do it. So it's quite interesting to see this potentiometer. Hopefully you can see it's got these little tangs of metal which are bent over the case. They're actually to hold it shut, but the little tangs are actually open on this one. So I'm not the first person to have a go at trying to repair this. Somebody's been in here in the past and they've tried to do what I'm going to do now, which is clean it out and try to sort out the contacts. So based on the fact that somebody's been in here before me and failed, that probably diminishes my possibilities of fixing this. Now of course it's not the end of the world, is it? It's just a 50k pot. We can certainly just find another one and put another 50k pot in, but as I said before, wherever possible I do like to try to keep things original, because once this has been replaced with a modern part, well it's then replaced with a modern part, isn't it? Now just taking a look at this potentiometer, I've never seen one of quite this design. Now you can see the wiper here, hopefully. I've got a wiper and I can see there's like a little cup on the end of this wiper, and the wiper looks as though it's got felt brushes on it. So the wiper isn't actually conductive, it's not actually the centre connector. What we've actually got here is we've got like a felt pad, and that felt pad presses against this well, it's like a spring material, it's like a shim of brass. So the actual connection point is done by this brass shim pushing against the carbon track. But hopefully you can see as I open and close that, it's it actually moves, it actually presses the brass shim against the carbon track. So you'd actually think that this is very reliable. And the way that they've done that is because with a normal pot, the wiper actually scrapes along on top of the carbon, doesn't it? Well, there's no scraping action. All it actually does is it takes this shim here and it just presses it against the carbon track. Have you ever seen a potentiometer like that internally before? It's the first one I've seen of this design. That really is a thing of beauty, isn't it? Talk about gilding the lily. So just feeling the way that the wiper presses down onto this brass shim, it really does have a lot of contact pressure. So I would have assumed that this pot should actually be super reliable. It's certainly got no play in the shaft. Well, that certainly seems better than it was, so I think we'll call that done. We'll have to see how we get on with it. When we get the thing powered up, it might be noisy and horrible. We'll give it a try. Hopefully this will show up on camera. You can see the shaft of our potentiometer here. Normally they just have a flat on them, don't they? But this has actually got a V cut into it. And if you actually look at the actual volume control, the grub screw on it is actually pointed. So the point actually engages on the V. So it makes for a very positive fastener. You can really feel that little point of the grub screw. You can find it just finds a V and it just centres perfectly. That feels better. It's certainly not squeaking anymore. So I'm trying to work out what the original colour of this wire was. Now I can see some red on it. Would it have been red and blue? Could have been red on one side and blue on the other. I can definitely see kind of a two-tone effect. I think it was red and blue. Maybe if we actually expose some of it here where it won't have seen the UV, it'll be clearer. Ah, there we go, it is. So the original wire colour here, it was this. I said it was a red wire that I've taken off here, but it was obviously red on one side with a blue tracer. So that's what we really want to put on. We want to put a red wire back on with a blue tracer. Well, I'm not going to have one of them, so we'll have to see what we can find. So this wire here is going to be our -9 volt grid bias connection. So what we'll do is the original wire was red and blue, so we'll just put a piece of blue tracer on here to identify it. Now I've got a wire here and all the insulation had basically just gone very hard and crumbled away. Now it would be easier probably just to solder a new piece of wire in, but again, in the scheme of keeping everything as original as I can, I'd rather just try to get some sleeving over it if I can. Well, fingers crossed that's going to be good for another 100 years. So I've just finished going through the resistors and I've just found one that needs replacing, and that doesn't surprise me because resistors are generally fairly reliable. But we might have to check them again because resistors can have other faults, so when we've actually got some HT on there, we might have to go back and check them, but I think we'll probably be okay. And as I've been going along, I've also been replacing some of the wires that would go to the battery. I've been replacing them when I'm working in the area of the circuit, and I've done most of them here. So I've just got a black, a yellow, and it looks like a red one to do. And I've been kind of stripping bits of main flex and whatever bits of cable I could find. I always seem to be generally lacking wire colours. So I think this is probably, I don't know, that might be one of the main HT ones. So that's the one we've got to do next anyway. And I'm actually going to use an old cord off a CB radio. That's what we've kind of been reduced to using. It's yeah, it's going to have to do. Yeah, I do suffer from a lack of different coloured wire. And for now I'm just going to put a cable tie on here, but I think we'll probably end up putting some kind of sheath over them to keep all these wires together, and I think before we're finished we're going to end up rearranging them slightly. But I just want to get them out of the way while we go ahead and replace the rest of these capacitors. And here's just the remains of the old sheath. It's a shame that wasn't complete, because we might have been able to have re-threaded this over the other wires. And it's also got one of the wires actually isn't a wire. It's just a piece of cord. It's a piece of string which runs through the middle of this bundle of wires. And in fact, there it is. And it's just actually to make it a bit stronger. Anyway, broken off now. So I've gone ahead, I have tidied up quite a lot of the chassis underneath, still got the capacitors to do here. These wires, I've done the job completely out of sequence, but you know, at the end of the day you can do this job how you want, there's no rule book. The reality is these wires are probably going to get in my way when I try to change the capacitors, but I was just in the mood to put some wires on, so you know, that's what I did. So we've got some wires on, and I've also gone ahead and I've made up some nice little labels for everything, so hopefully when we get the battery we don't blow it up. So I'm just going to plug it in, and we're going to look at the I'm going to run the heater, the filament supply. I'm going to run that from my bench power supply. So let's plug some valves in and see if we actually get anything. Now with these DC sets, they actually don't draw an awful lot of current. It's you know, they're probably about 100 milliamps a valve, and if you're expecting these valves to, you know, get hot and start glowing like they do in a mains set, well, you're in for a disappointment. They don't glow and they don't even get warm. I think that's it. Oh, it's not drawing any current at the moment. Maybe it's off. Yes, it is. Okay, so we've got our first valve in. And that's drawing 170 milliamps, so it's drawing more than I said, isn't it? I said 100, it's drawing 177. Let's get another one in. And that's put another 100 milliamps on that. So we're at 266. And let's put the final valve in, which is this one here, V1. Which is our RF amplifier. Incredibly simple sets these. I think I said earlier, valve number 1, that's our RF amplifier. Valve 2 is our simple detector, and then valve 3 here is our audio amplifier valve. So it's kind of the equivalent of a free transistor circuit. You really couldn't get any simpler than this, could you? Okay, let's plug this one in. And 350 milliamps. The actual data sheet for this radio says it'll draw about 400 milliamps, but I think we're pretty close there, so all that's looking good. So I'm going to start now removing all these capacitors, and we're going to start with this capacitor, which is C11. Watching me changing out all those capacitors is really going to be quite boring. Well, what's new with my videos? But I think what we'll do is we'll leave the old fart knocker to get on with it, and we'll come back a bit later. Now, I know some of you have made some excellent suggestions, and you were talking about building an AC/DC power supply, and of course we could do that, but on this occasion I've decided not to. I actually want to build a battery for it because it is a battery set. So I've gone ahead and I think I've bought the world's supply of batteries here, so let's see what we've bought. And I'll tell you what, let's go for this one first. So what we've got here is a big pack of Energizer PP3 batteries. Oh, they don't seem to call them PP3s. Apparently the correct Sunday name is a 6LR61 9-volt battery. I'm going to call it a PP3. It is a PP3, isn't it? Let's have a look in the box. So these are the industrial range. I don't know if they're actually any different than the standard ones you buy in the shops. They certainly seem to be a little bit cheaper. I bought these on Amazon. Let me see how much they were, because I'm sure some of you might be interested. So we paid £11 including delivery, and I think there's 12 in this box. So we actually need about 13.3 batteries to give us our 120 volts, but of course you can't install 13.3 batteries, so we're going to use 14 batteries, and we're going to use, if we use 14 of them, I think that gives us about 100, what does that give us? It gives us 126 volts, so we're slightly over our 120, but that'll be fine, that won't make any difference. Should we have a quick look at them? So there we go, so we should have 12 batteries there. Count them, so let's just check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe I should have bought another pack, but I think I can find some other 9-volt batteries. Let me see if I can find some lying around. And here's another two. Unfortunately, the Duracells. I'm not sure about introducing Duracells to this crowd. Yeah, a different colour. Might start fighting or something. So I'm not sure. What should we arrange them in? What shape? I think it's going to be something like this, isn't it? Yep, so it's going to be an arrangement, something like that. And because we bought all these batteries, of course, I've got all these battery clips. There was actually an option to buy some battery clips that the cable exited at one side, and I kind of wish I'd done that now. Now the other thing that we're actually going to need is, apart from the 120 volt tapping, which is going to be at the end of the series assortment, because we're going to wire all these up in series, we also need to wire up our screen grid. For some reason I wanted to call it a suppression grid, something a bit different, a suppression grid. Why do we need a suppression grid? Because somebody decided to install screen grids. That's a whole different story. Anyway, waffle. So we actually need, on the fifth battery in, which will be 45 volts, we actually need to make that one our screen grid output, so we must take a tapping off there, so that'll be 1, 2, 3, 4, 5, so that's fairly easy. Okay, that'll do for one pack. So what we'll do now is we'll make another set of them. Quite enjoying this, it's very Blue Peter. I just wish I had an old cornflake packet and a couple of egg boxes and some glue, and I'd be in my element. Yeah, that's what I should maybe be doing, making stuff with egg boxes. It's about my level, that, I think. Right, there we go. Egg boxes and perhaps washing up liquid bottles. And a dash of solder. Bit of a trim. Put some heatsink on there, and then it's just another 14 to go. Okay, that's going to be fun. I like doing jobs like this. You know, just switch off and plough on. I think we'll put a bit of tape round. Now we've made these two little cartons of batteries, I think we'll just go ahead and put them together. Right, I think that will do. So let's get going with this one again. So we said that's going to be our negative there. That's going to be our positive, which we have to turn round. Oh no, we don't, do we? Yeah, that's that way around. And we've already soldered that, so let's just put some heat shrink onto it. We need heat shrink. Heat shrink, we've got every size apart from the one I actually need. So I'm going to carry on doing this up to battery number 5, which should be our 45 volt tapping, and when we get there I think we'll take a look at that and we'll do a voltage measurement, I think. Well, fingers crossed, I'm hoping that we're going to have our 45 volts. Probably won't be exactly 45 volts, I'm not sure how much these batteries not being on any load will affect it, but hopefully we will be in the ballpark for our 45 volt screen grid. And we're measuring 48.9, well 48.19, so that looks pretty good to me. Let me go ahead and finish wiring all the rest of them up, and we should get our 120 volts. So as you can see, we went ahead and I finished connecting up the batteries, and we're actually slightly above the 120 volts that we wanted. But that isn't surprising, because for one thing we've got an extra battery in circuit, and another thing is these batteries aren't loaded. It's effectively an open circuit voltage. It will pull down a little bit when it's actually running in the radio. But I'm not too worried about being slightly over voltage, because the anode on these valves is plus 200 volts, and all the capacitors we've got in there, they're all above 200 volts. They're 250 or 1000 volts, so no problems with them. So I think we'll stick with that. And I think we are going to try to treat this battery with a little bit of respect, aren't we? Because we've got enough. We have got enough voltage there to get a little bit of a tickle off it. Kind of makes me wonder how long ago the last person was to get an electric shock off a high tension battery. It must have happened all the time back in the day, mustn't it? Well, I've got some more batteries here, because I'm sure you remember we need more than just the high tension voltage and the 45 for the screen. We also need our two grid bias voltages, and the grid bias voltages are -9 and -4.5. So I just remembered that back in the day you used to be able to buy these, I would call them cycle batteries. You used to have the you used to have one of them little dim lamps. They were rubbish, the little lamps you used to have on the front of your rally grifter, and yeah, they were totally useless. You used to cast a little horrible pale yellow light out. Yeah, useless. Anyway, they used to have these batteries in there, so I'd probably call this something like a lantern battery. And I didn't even know that they still made these, but obviously they certainly do. I haven't seen these inside cycle lamps for many years. I'm sure they've gone on to different batteries when they started using LEDs. So let's get these out. So as you can see, these are made by Energizer, aren't they? And I think it says on the back here they're actually, like everything else, made in China. So I suspect we're probably going to bung them on the end of here somewhere like that. That'd probably fit quite nicely, wouldn't it? But we do have to turn them round, and we've got to link a couple of terminals together. Now I suspect these grid bias batteries are much larger than we actually need, because the actual grid bias current, it's actually a tiny amount of current. Valves don't take a lot of current to operate. Basically they're voltage operated devices, so current is not really that important to them. Okay, I think that will do for that. So what we've got to do is we've got to link two of these terminals together. I wonder if I can put a fold in them and just bend them over, something like that. Sort of might seem possible. And I think we'll do it like that actually. I think we might just put some solder on there. Nope, got a bit of a fail there. Solder doesn't seem to want to take to them. Let's just see if doing the same thing again changes anything. No, I'm totally failing with that. This metal doesn't seem to want to take solder at all. I wonder if it'll help if I roughen it up a bit. That's the only thing I can think to do. No, I'm totally failing at that. That's a waste of time. These must be made out of stainless steel because although I've really cleaned them up and tried a couple of different types of flux and got them really quite hot, nothing's touching them. It's just rolling off. The solder just beads off. It rolls off like water droplets on oil or something. This thing weighs like a pound of lead, and that's probably because it's a lead acid battery. So it's got a name on here, which is a cyclone cell. And back in the day, you used to find these cyclone cells. They tended to be much bigger than this. You used to find them in things like uninterruptible power supplies, UPSs. They'd be a bigger size, probably like twice as fat and twice as high. Now, in some ways, even though this is only a 2-volt battery, I'm probably more fearful of this than I am that 120 volts of HD, because the thing about lead acid batteries, they can deliver an absolutely frightening amount of current, and they certainly present a fire hazard. You don't want to short them out. So I think one thing that I will be doing when I actually put this in my little battery box, whatever we end up making, I think it'll almost definitely have some form of inline fuse in it. We're going to have to fuse it. And of course this 2-volt supply is going to be the filament voltage, the filament supply for our valves. So it's 2 volts and it's actually 8 amp hours. I seem to think that the actual original lead acid, like these glass bottle cells that they used to have in valve radios, they were actually quite a high amp hour. I seem to think there was something like 48 amp hours or something like that. Certainly I've seen radio batteries up to that kind of capacity. Now unfortunately this is only an 8 amp hour battery, but given that our radio only draws about 400 milliamps of current, we're still going to get a little bit of time out of here. And of course what we can always do is we can strap a few batteries together if we need to, but I don't think this is a radio I'm going to use very often, so I didn't want to spend too much money, because this battery on its own was, I said it was about £15, wasn't it? So this capacitor is measuring 2.6 microfarads, and it's actually rated as being a 2 microfarad capacitor. So it seems to have gone up a little bit in value, but the actual tolerance of these would have been very poor anyway. So in terms of capacitance, this looks fine, but of course what this tester isn't doing, it isn't telling me what the leakage is. Now, because I don't generally bother to test capacitors, I just replace them on site. I don't actually have one of those funky high voltage capacitor leakage testers. I particularly do like the ones that have got the green magic eye, but I don't have one. If I come across one, I'll get one at some point, but I haven't got one so far. But what you can do is, you can just use, do a very crude test, you can just use a DVM, a digital voltmeter. So these couple of leads here, these are just connected to my benchtop power supply. In theory the higher the voltage the better, but I'm just using 32 volts because that's what it goes up to. So I can just show you that. Let's just clip these onto the voltmeter. And it goes up to 32 volts because all I'm doing is I'm just measuring my supply voltage there. So what we'll do is we'll just disconnect that, and remember the whole point of a capacitor is to block DC. So if we actually put this into circuit, it is going to pass some current while it charges, but once it's charged up it should actually stop. So what we'll do is we'll just clip that on there, and you can immediately see that this goes up to 31 volts. Now the reading is falling as the capacitor charges. What we can do is we can just speed the process up a bit charging by just connecting the other supply leg to it. So let's just charge it up to the full 32 volts and take it off again. But again, the meter is still indicating 31 volts. Now the voltmeter reading here isn't really what's important. This is a comparative technique, so don't really get strung out by the actual voltage level. The fact we've got a reading on there means that there is some current flowing through this circuit, and if this capacitor was doing its job there would be no current flowing, and if there was no current flowing this would be set at 0 volts. Well, it isn't, is it? So just to kind of prove that, here's a capacitor of the same size, approximate size. I'm going to put that into circuit, and initially you are going to get a high voltage reading, but that will drop quite, well I say high, it's actually 1.3 volts, it's charged up immediately, and that will continue to drop. We can actually speed the process up by force charging the capacitor, so I'm just going to force charge it there. I'll just get that on there. And you see our voltage there has pretty much dropped to 0, so there's no current flowing in our circuit now because the voltmeter reading is, well, it's 0.003. There's no current flowing in the circuit. So let's just put the wax capacitor back in. Again, just to be fair, I'm just going to force charge it just by connecting it across the supply. And I charged it right up there. You see the voltmeter drops to 0 when it's fully charged. As soon as I take it off, it goes back to 30 volts. So this capacitor's leaking. We've got current flowing in our circuit, and got some other capacitors here that we can just try. Again, that one's leaking. And that one's leaking. So we've tried 3 of these vintage capacitors and they're all actually leaking. Again, let's go for a modern capacitor of the same value. What are these? I think these are 0.1, another 0.1 here. So let's try that. And of course you've got no voltage reading here. Go back to one of the valve ones, the old ones. Back up to 30 volts. So, as I say, don't get strung out by the actual voltmeter numbers on here, the actual voltage level. The fact you're getting a number shows you've got leakage. The higher the voltage, the more leakage you've got. I'm hoping you can see here, you've got a junction point here, and they actually make these junction points just using a little kind of like a coiled spring of wire. And what they would do is they thread the various components through the centre of the spring, through the centre of the coil, and then they just put some solder on to solder them together. So what I've done is I've gone ahead and I've made one of these little coil springs, if you like. I'm going to slip that on, and then we're going to slip our capacitor leg in there, and then hopefully we can get our coiled spring back up, something like that. And now I'm just going to run some solder between them and hopefully it won't fall off. And there we've got a joint that looks just like the original one. So there's our first capacitor soldered in, number C11. Just got 6 capacitors to go. There is actually some other capacitors in there. You can see that one down there. That's a capacitor, and there's one lurking under there, and well, just these 2 I can actually see. These capacitors you can see down here, these little flat brown things, what they are is they're actually mica capacitors, and they tend to be very reliable. Oh yeah, there's a more visible one there. So that's a mica capacitor, and you know, with a bit of luck you won't actually have anything wrong with that. I've just noticed that when this was assembled originally, these mica capacitors have got little mounting holes on it, and what they've done is they've threaded through the wires, one of the wires here, they've actually threaded it through the one of the mounting holes for the capacitor, I guess just to stop everything blowing around in the breeze. That's quite funny, and I think that's probably a logical place to leave it for today. So until next time, I think that'll do. Hope to see you again very soon, but until then, bye bye for now.